This is a lecture course on synchronization. Part 4, Phase Difference. To remind you, synchronization of periodic oscillations means that as a result of interaction, the timescales of coupled systems do not simply change, but are rather adjusted in a special manner. Namely, the timescales become either equal or rationally related. This means that their ratio is equal to the ratio of integer numbers. However, there is more subtlety in how synchronization manifests itself in real situations. Consider tiny 1 mm long worms called C. elegans swimming in water. These worms swim by wiggling their bodies in a rhythmic oscillatory way with a certain frequency. Of course, all worms are slightly different, most obviously in length and in thickness, and their natural frequencies of wigglings are slightly different too. But when two worms are swimming very close to each other, they feel each other's presence through a number of mechanisms: through the waves created by their neighbor, which reach their bodies, through occasional collisions, and through some chemical interaction. Apparently, it becomes more pleasant, less difficult for them to swim in such a close proximity to each other if they synchronize their bodily movements. It appears that if these worms are very close to each other, they swim by aligning their bodies perfectly, as shown in this video. This corresponds to the so-called in-phase synchronization. However, if they are allowed to swim far away from each other, their frequencies can still be the same, but their bodies can be antiphase. The video here shows how the style of synchronization changes depending on the distance between the worms. When the distance is large, which corresponds to the far right position of the blue circle in the lower panel, the worms swim in the antiphase manner. When one worm bends upwards, the other bends downwards. However, when the worms come closer and the distance decreases, which corresponds to the blue circle appearing in the far left position, the worms swim in phase. This means that they bend their bodies in the same manner at every time moment. The previous illustration leads us to the idea that we need to find a way to somehow quantify the different versions of the same kind of synchronization. To do this, we introduce the idea of a stage of oscillations. Consider a mechanical pendulum clock attached to a beam. Intuitively, we can assume that when the pendulum is, say, in its far left position, it is in the beginning of an oscillatory cycle, at zero stage. After one full oscillation is completed, it is at the end of the given oscillatory cycle, at the final stage. When oscillations continue, all the stages are repeated again and again. Note that when the pendulum sways, it makes the whole clock slightly sway too, and this in turn makes the beam to which it is attached swing to and fro by a small amount. Now suppose there is the second clock attached to the same beam. From the way the beam vibrates, it learns about oscillations of the first clock. Also, through the same mechanism, it sends information about its own oscillations to its neighbor. This is how the coupling between the clocks works. This animation illustrates the case when no synchronization occurs between the clocks. Their pendula swing independently of each other. When the left clock is in its far left position, during various oscillatory cycles, the second clock can be at any position. This animation illustrates the so-called in-phase synchronization. Both pendula swing together and are more or less at the same position, at the same stage, at any time moment. Here we observe an antiphase synchronization. When one clock is at its far left position, the other is at the far right one, and vice versa. When one pendulum moves to the left, the other moves to the right, and this continues throughout the whole process. This animation illustrates the case when synchronization occurs, which means that both pendula are making a full oscillation within the same time interval. However, they are neither in phase nor antiphase. Namely, every time the left pendulum is at the far left position, The right pendulum has already covered part of its way back to the right, and oscillations persist in the same manner forever. Now, let us formalize the idea of a stage of oscillations and introduce a quantity that characterizes the stage of every oscillatory cycle numerically. This quantity is called a phase. In the pendulum clock, we assume that after one full swing, the pendulum returns to the same physical location, but its phase increases by 2 pi. So during one swing, the phase grows by 2 pi exactly. It makes sense to assume that when the pendulum is at its far right location, the phase should be a half of 2 pi, that is equal to pi. At any other position of the pendulum, the phase takes some value between 0 and 2 pi. Importantly, the phase should be growing monotonously with time and is not allowed to decrease or to fluctuate. Consider a biological example, a human electrocardiogram, which shows the electrical activity of a human heart. Sharp high peaks here, called R peaks, indicate the moment of a new oscillatory cycle. But the time intervals between the cycles vary due to the natural heart rate variability. We can assume that within an interval between the two consecutive R peaks, the phase grows by 2 pi, and it should be growing monotonously. How exactly it grows depends on how we define it. For simplicity, let us assume that the phase grows linearly. The formula expressing how the phase phi depends on time is given to the left of the ECG. Here, small t is time, small t number I is the moment when the ith R peak occurs, and capital Ti is the interbeat interval, which means the interval between the moments ti plus 1 and ti. To find the phase of every new oscillatory cycle, we take the phase at the end of the previous cycle and add to it the value by which it grew since the previous cycle finished. The resultant graph of the phase looks like shown here. The phase is a piecewise linear function of time which grows monotonously. Importantly, the derivative of the phase is inversely proportional to the instantaneous period Ti of oscillations and has the meaning of the instantaneous frequency Fi multiplied by 2 pi. Note that this phase is not continuously differentiable at all times. Its derivative jumps by a finite amount at the moment of going from one cycle to another. It might be desirable to introduce a phase in such a manner that it is differentiable at any time. This can be possible using a slightly different approach. Imagine that our periodic oscillations are represented by a limit cycle, which can have quite complex shape shown in the left-hand figure. Mathematically, we can assume that there exists a change of coordinates which allows to associate every point of this complex cycle with exactly one point on some closed curve of a simple shape, which can be drawn on a plane without self-intersections, as shown in the far right figure. This transformation should be such that the simple closed curve embraces the origin. Then, for every point on this simple closed curve, we can introduce an angle phi according to the formula shown. Here, y1 and y2 are the coordinates of the point on our simple closed curve on the plane, and arctan 2 is an extended arctan function. Let me explain how it works. The usual arctan function of an argument y2 over y1 takes values from minus pi over 2 to plus pi over 2. The use of this function would be inappropriate here because the difference between the largest and the smallest values of arctan is only pi. But we need such a function which would take values between minus pi and plus pi to ensure that within a single cycle the phase grows by 2 pi. This is achieved by using the extended arctan, arctan 2. This function depends not only on the value of its argument, y2 over y1, but also on the sign of the denominator y1. For a positive value of y1 over y2, If y1 is positive, arctan 2 coincides with a simple arctan. However, if y1 is negative, arctan 2 takes values from the lower branch of the graph. Similarly, if the argument of arctan 2 is negative, but y1 is positive, this function coincides with arctan. But if y1 is negative, we choose the upper branch of the graph. Just like for the first phase, to ensure that the phase grows monotonously, to find the phase during the cycle number I plus 1, we take the value of the phase at the end of the cycle number I, equal to 2 pi I, and add its increment since the beginning of the current cycle. This picture shows the second phase marked by a red curve against the first phase marked by dashed blue line. Both phases were introduced from the same experimental signal, and the parameters were chosen such that the beginnings and the ends of the oscillatory cycles coincided for both phases. Just like the first phase, the second phase grows monotonously. However, unlike the first phase, it is differentiable at every point. Like the first phase, during a single oscillatory cycle, the second phase increases by 2 pi, but unlike the first phase, it grows nonlinearly. Introduction of the phase allows us to characterize synchronization quantitatively. Consider one-to-one synchronization. Suppose we introduced phases phi1 and phi2 for both interacting systems with any of the two methods discussed. Now, to assess the presence or absence of synchronization, we can construct the phase difference, delta phi, as a simple difference between the two phases. The phase difference changes in time. When plotting the phase difference, it might be convenient to divide its values by 2 pi, as done in the figure shown. We say that synchronization takes place if the phase difference demonstrates a reasonably long plateau of a certain thickness epsilon. Within the time interval during which this plateau occurs, there is a one-to-one synchronization, which we call phase synchronization because it is detected from the comparison of phases of interacting systems. Mathematically, the condition for the existence of the plateau can be described by the following inequality, which basically says that the distance between the phase difference and a certain constant c should be smaller than some number epsilon multiplied by 2 pi. Note that epsilon should be a reasonably small number, and it is usually chosen to be less than a half. Importantly, if the oscillating processes are non-stationary and/or affected by random fluctuations, synchronization is likely to occur not all the time, but only during some finite intervals of time. If to detect synchronization in such cases we only use the spectral frequencies, we will not be able to say when exactly synchronization is happening. However, the phases allow one to determine not only the presence of synchronization, but also when synchronization occurs. To detect synchronization of a different order, we can still use the phases of interacting systems. However, the phase difference needs to be constructed with account of the suspected order of synchronization, which is the ratio of two integer numbers n and m. Namely, we take the phase of the first system and multiply it by n over m, and then subtract the phase of the second system. An example of the phase difference between the human electrocardiogram and the breathing process is shown in this picture. Here, we suspect that the phase synchronization of the order 1 to 3 is taking place, and we wish to find out if this is true or not. We can see two plateaus of phase difference, which suggest the presence of a 1 to 3 synchronization. The thickness of each plateau is definitely less than 0.5. Therefore, we can state that during the observation time of 180 seconds, there are two episodes of 1 to 3 synchronization between the heartbeats and breathing. I would like to acknowledge the professional and technical assistance from Olga Sosnovtseva and Dmitry Postnov.